Okay guys, I think we have to start. Apparently the box cannot be open and the speaker therefore not workable at the moment. So I will have to keep shouting. Okay. Okay. I hope you do well in mid exam. Well, I really hope so, because in the second half, and today will be the beginning of it, it will be shown that you need to work for the first half first before you can actually start on the second half. Meaning the calculation will be at least double. Okay? In terms of knowledge, in terms of equations, there will be not a lot of added equations. There are no added supports. Okay? It's more about the understanding of how material behave. Okay? So let's start. Today, in the second half, in the first half, what we do is what we call external forces. The forces that is outside the body. For example, apply load, apply moment, those are external. The reactions actually happen where the body contact to the support. So in fact it is outside the material. In the second half, what we will look at the forces happening inside the material itself. Okay? So that is where the word internal forces come from. The forces that happen inside the material. Okay? Today we'll talk about what they are first. Why do we have to study it? Then we'll talk about this type and definitions. How do we define them? Then we'll separate the two cases, 2D, two-dimensional, and three-dimensional. Then we'll start on two calculations. Okay? Well, bear in mind that we will actually live in 3D worlds. This calculation, these practices, is just so that we can get certain answers. We start to understand it. But never forget that we are in 3D worlds. Okay? The practice that it will be, however, in 2D only. Meaning we have less feature to look at. Okay? Let's say we have just a structure, just a beam, 1 point load. Okay? We should know by now how we calculate reactions, right? The body takes the force, it's stable, it's in equilibrium, it doesn't move, it is in static. It means that there must be other forces to balance off or other movement. In this case, then we have reaction at point 1, reaction at point 2. Okay? We learned how to calculate them already. Now the question is, how can this force all of a sudden transfer here and transfer here? Right? The system here, it looks like there is only one force. Okay? What I meant is, if this force is 0, that will be 0, 0, and that will be 0. Correct? Therefore, it means that these reactions actually happen because that point P is not 0. That point load P is not 0. Right? So, there must be a way that point P can actually spread out both sides. Okay? If it spread out this way, then it becomes R1X and R1Y. The applied load spread out that way, it turned out to be R2. Right? So there must be a mechanic that actually can transfer from point load in the middle, not really in the middle, somewhere in between. Right? And then spread out both sides. Okay? Then, in that case, let's think about this. Right? If I designate point A, I change the color to blue because assuming that we already know how to calculate those three reactions, meaning we can calculate it. Once we know it, we just change the number, the color to blue. Okay? Now, let's say we calculate R1X, R1Y, and R2 already, and then we look at point A. I want to know, my guess is, and I think you can understand, my guess is that point P doesn't jump from in the middle to both sides. It actually moves along the material. Correct? It transfers from load P in the middle, transfer left hand side and right hand side. Correct? So it has to go through that material, in this case the beam. Right? So Let's look at point A, just a point on a beam, okay, and do what happened. Now if I want to see the force at point A, what do? We go back to the concept of free body diagram as usual, okay, we just separate them out, okay. Then I can separate this into two free body diagrams per se, that one, okay. If we look at this picture, it means that is a body, right, and these are environment, correct. Therefore there must be forces here acting on it. I haven't drawn it yet anyway, right. This part is same, it means that from here to here is the body, right. If we look at this picture, then it means that we consider this part environment, right. The contact between the body and environment is at point A, there must be forces here, okay. Don't forget that we always say that the reaction comes from the condition of the contact, okay. This contact, however, we haven't studied yet, right. So let's talk about what it actually is. If we look at the left hand side picture here, okay, this is the left hand side picture here. For that left hand side picture to be able to be sigma fx equal to 0, right, there must be a force acting to resist R1x, correct, right. In this case, where is the force? The force is therefore must be from the contact point, this contact point here, right. So using equilibrium, concept of equilibrium, it means that there must be a force here resisting it from moving to the left hand side, right. The same way, if we look at this picture here, still on the left hand side bottom, sigma Fy is not 0, correct? But we know that in usual case, the whole body is stable, right? Staying still, meaning there must be a force pressing down, right? To resist it. In this case, it comes into that form. Okay? Is it in equilibrium yet? No. Why not? Because apparently that R1y and that VA create what we call a couple of force. If there is a couple, meaning there must be a moment, right? This body without movement resisting it, it means that it's going to rotate in a circle, right? Therefore, there must be certain reaction happening inside the material again, that is in the moment form. Okay? There. Three unknowns. This is 2D. I have to emphasize this is 2D. Now in this case, we can guarantee equilibrium, right? Now we know that point A, we separate it left and right. These forces happen because that is the body, that is the environment. So the environment acting to the body with these forces, correct? Action, reaction. If something acting toward the body is actually acting back, right? However, our body here, when it does, we don't draw what it does, we draw what it was done to, right? So that force actually equates to that part, okay? Therefore, this part should have three forces as well. Two forces, one moment, there. Equal and opposite, therefore using the same name. Okay? Now this is we explained by equilibrium. What does it mean by physical? Okay? Note that there are three of them. I will explain it one by one. Okay? So, I will show it using a pen. Okay? Hang on, let me change this screen out. Where is it? This is two pens, right? What we will compare, what it means is that we look at this point, okay? This is like normal material, continuing, correct? And then we'll look at this contact, that contact there, here, and see the difference, right? Remember what I said is there will be a force in the x direction, okay? This is the reason why, look at this point, if I try to pull the point apart, I cannot, correct? Compared to if we only touch. If I want to pull it out this way, it can separate, correct? What different is this? This part doesn't pull this part, and this part doesn't pull this part either, correct? Therefore, I can just separate them. On the other hand, if the material is just one piece, real material, right? I cannot pull it apart. because that part will pull that one back in, right? And that one will pull that part back in as well. Okay, so that become that force that I call N. I use symbol N for now. Okay, then we have the vertical force. Physical meaning the same. Still looking at this point, if I try to slide it one towards you and one back to me, I cannot, well, up down in this case from the board, right? Then I cannot do it, right? Compared to just touching it, if I slide one up, slide one down, it will be that way, right? Separate simply. The reason is the same. If you just touch it, this part doesn't pull that part, and that part doesn't pull this part, right? So it can just separate. If, on the other hand, normal material, you cannot slide them. It means that this part was pulled back by that part, and that part was pulled back by that part. Okay, that force we show as V. The last one is the moment. Remember that moment, because normal touching material, if I want to rotate it about this point of contact, I can. You see the angle, right? Because again, it doesn't twist each other back. If the whole material is like that, then that way I cannot make an angle at this point. If I can, then the pen would have been broken. Correct? So this is the physical meaning, and that is relating to the forces we have to calculate in 2D. Those three. This one are the one that make sure that they don't separate N, right? That one is the one that makes sure it doesn't slide up down. That moment is the one make sure that it doesn't actually rotate. Okay? These three pairs, each forces is a pair, right? Are equal and opposite if it at the same point. Okay? Let's talk about the definition then. We have seen in 2D, we have seen three types. Okay? Three forces. Now let's talk about how we define them. Okay? And then we will talk about the definition or directions. We actually define them by the movement of cross section. Okay? Demonstration, I will use rubber. This rubber, okay? I draw two lines because what we will define our internal forces depend on what's happening with those two lines. Those two lines are not doesn't represent lines though, don't represent line. They represent the whole cross section, right? I draw the whole line all over, right? Meaning, in fact, if you cut it through, you can see cross section here, like that. Okay? The first internal force that we're looking at is what we call axial force. Okay? There will be the letters showing later, axial force. What it does is that, looking at these two lines, the force will be on the line of the member. Okay? Then if I pull them apart, notice these two lines, they move out. From here, they move out. If I actually press it this way, then these two lines get closer. Correct? These are the mechanism of axial force, meaning it makes the cross section going away or going into each other. Okay? Notice the cross section, the line keep parallel. It doesn't rotate anything. It just moves out or in, right? Those are defined by axial force. Okay? Or pull out. Okay? The second one is what we call shear force. Okay? Shear force is the one that goes vertical in the picture, but in fact what we do is we relate to again the cross section that we cut. In this case, what it does is slide the line up and down. Okay? Just that. Meaning these two lines, cross section, the shear, what it does is slide it this way or this way. Okay? Notice the movement is always opposite. If it going apart axial, one left, one right. One left, one right. This one is called tension, this one is called compression. Right? Shear force the same, one up, one down. It cannot go up together. It doesn't have any internal force because the cross section doesn't move away from each other. Okay? Then the last one is the moment. The moment, what it does is that it bends the structure. Okay? It bends the structure. Okay? If you look at the cross section doesn't move. In fact, cross section rotates that way and that way. Okay, look again. There, and then that one. Okay, so that's the definition and direction that we're looking at. Just revise on what we just said, what I just said. In 2D, we look at three of them. The first one is the one that pull the element apart and then or compress it in. Notice the line is on the same line. Okay, this definition is the line of the member, meaning if we change the line of member to that, into this one instead, axial force no longer this line, right? Because definition is that it must pull these two cross sections apart. So in this case, axial force will go this way instead, meaning on this line instead. Okay? So that one. This is, the name is the axial force. Now when we calculate these kind of things, we tend to give direction as well, correct? Drawing that is not too bad, but it's long. So what they do is that rather than drawing this box, they actually use the word tension or sometimes use just T. I personally just use T. If it's compression, แรงอัด then compression C stands for it. Okay? The shear force, however, doesn't have a name. The symbol they usually use is N. Why is it N? I have already said that if it's N, it tends to come from the word normal angle, 90 degrees to something, right? In this case, the force is 90 degrees to the cross section. Okay? Again, that's why it's defined by cross section. Okay? That force is this way, 90 degrees to the cross section. Okay? The shear is parallel to the cross section. Okay? That is the shear force. Apparently there is no name for them. But notice, this one has to be opposite. If this one is up, this one must be down. Right? This one down, this one up. Always opposite. Okay? They draw the box in this case, there's no name for it. Okay? The last one is the bending moment. I tend to use symbol BM. In the book, I have to say this, in the book they use only M. I find it confusing for you guys to separate between the reaction and the bending moment. They are two separate things. Okay, so I change the name. But you can use M if you want, no problem. I can understand it. Okay, that is the bending moment. Then the symbol is come from the bending. Okay, the first one on your left hand side is bent in this picture. Notice the smiling face. Seriously, they call it smiling. Okay, on the other side is this way. You see the sad face, and therefore that is the symbol they use. However, the smiling and the sad face is a little bit restricted because it's only in the horizontal way, right? If you have a member that incline, you have to describe how you smile as well. You smile a bit more cutely, something like that, right? So rather than doing that, what they do is they add this symbol for smiling and that symbol for sad face. You can use either. Okay? It's just to make the symbol draw quicker, that's all. Okay? Now before we move on, we have defined the 2D internal forces already. Right? We have one axial force, we have one shear force, and then we have one bending moment. What about 3D then? Okay? The same piece of material, but now we consider all possible motion. Okay? The first motion is the same, it's the axial force. There is only one way you can move the cross section away from each other, is that line. Okay? So in 3D it's still one axial force. What about shear force then? Of course, whatever apply to 2D apply to 3D as well. We have the up down. Don't forget the word sliding it, right? So in this case, up down still count. However, there is one more axis that you can slide it. You can slide it back and front. So in 3D, you have one axial force, but you have this one shear and that is another shear, right? Notice that the force comes with the axis x, y and z, but no longer call fx, fy, fz because it will be defined by the material, right? So there we have one axial, one shear, the other shear, two of them. Okay? The moment then, right? We talk about the moment, the bending moment already, right? Notice the bending moment in 2D come about z-axis, correct? That one, the smiling and the sad face. If it's about y-axis, right? Meaning it go that way and that way, right? You can notice the cross section, it probably go that and that, right? So there is two directional bending moment, okay, two of them. The last one, the moment for the last one is the one that go about x-axis, right? It's this one. Notice the movement of cross section. It doesn't rotate the same way, right? Bending moment rotate this way, correct? Torsion rotate this way, right? Different mechanics. Therefore, that one is called torsional moment. It doesn't create smiling or sad, it's twisting it, right? Okay, different mechanics. In terms of calculations, the 2D, you have three of them. In 3D, then you have six. The axial force, one of them, two shear forces, two bending, one torsion, and two bending moments. Notice the axis x. Axis x is not defined by horizontal or vertical. Axis x in this case defined by the alignment of the member. Okay? The same answer, the same thing all over again. So again, since we are just beginner, we're gonna do 2Ds, okay? But at least the picture should stuck in your head. Can I move on? Let's look at some example, shall we? Just simple beam, two supports, okay? What we want to find is that what is happening at point A, internal force at point A and internal force at point B. Okay, one point load. Okay, so simple, you can close your eyes and do it. Close your eye, not close your eyes. Okay, you can close one eye and do it still, I think. Okay, there. To find this, apparently we still need reactions. So I emphasize, if you suffer with mid-semester exam, revise quickly, because you will suffer even more if you don't recover. Because then we need to find reaction first before we find internal forces. Okay? Just going quickly, I can use sigma moment about 0.1 and then I get the value of R2. Once I get value of R2, I can use sigma fx, then R1x will be found. I can actually take moment about 0.2, or I can use sigma fy, then I get R1y. Okay? So equation, I like to go through this quickly. Okay? That's normal system. Oh, I forgot. I haven't posted yet, have I? Sorry, I forgot. I was a little bit head in the crowd this morning and yesterday evening. Okay, I will post it maybe at the end of the day. Okay. Well, the equation was given. You probably have to find your way through it. Okay. Now then, notice the way I actually write down my distance. This is what the equation gives you. 2.5, 0.511, right? Because we have to define where point A is, where point B is. When you calculate, I don't need that 2.5, 0.5. All I need is that from here to here is 3, from here to here is 2. To calculate reaction point A, point B doesn't mean anything. So for this picture, you can ignore it for now. Okay? Then once you calculate it, now we want to find the internal forces at point A, specific point, right? So what we do, we separate the free body diagram, okay? In this case, I will choose the left hand side, separate it, then I draw from 1 to A, not from A to 2, from 1 to A, okay? Now we know that we have three internal forces. These are the calculated R1X and R1Y, right? So, draw it in, and then the same thing happening, sigma Fx, sigma Fy, sigma moment. Okay, which one is most appropriate? Then do that one first. This one here is quite simple, x, y, z, right? So go sigma Fx, then we get the value of Na. This calculation will show you Na equal to positive. What does Na equal to positive means? Yep, the same direction as we draw it, correct? Meaning it's actually going that way. The next question is, we do not say left right. This is axial force, correct? Internal forces, we don't say left right. This one here, we have to say axial force must be compression or tension. Is it compression or is it tension? Compression. Very good. Kilonewton, compression. Right? Sigma Fy equal to 0. Simple, only 40 and VA. There we are, 40. Unit, kilonewton. Positive meaning, this one here is actually down. Correct? So, since there is no name for it, we just have to draw that box. Right? Notice that box. That one is on the right hand side of the box. Correct? Therefore, that one will match with this one on the right hand side of the body. Okay? If that one is down, we already know it must be opposite. If that one is down, then that one must be up. Okay? Then we find bending moment using sigma moment about point A. And then we get 100 kilonewton meter. Right? Normal unit. Now, if it's positive, it means that it actually go that way. If it go that way, it means that that one twists that way, that one twists that way, creating smiling face. And the symbol will be given as smiling. You can draw the box, I don't mind. You can write smiling, I don't mind. Okay? But I think just drawing it is much quicker. That's all. What about point B then? The same concept repeats itself. Don't forget that you only need to see point B. You can cut A and B, fine. Okay? But I don't like it. I usually tend to use from point 1, from support to the point I cut. So in this case, this is the picture I would draw. Notice 1, meaning there will be series of explanation going on here. Okay? On the left hand side, that is R1X, R1Y. Right? At 3 meters, there is only a point load, 100 kilonewton. Then we have 3 internal forces. This time it happened at point B. So VB, NB, and BMB would be nice. Right? So we know exactly where it is. And the system now create the same. It's one by one. One unknown in X, one unknown in Y, one unknown moment. So sigma Fx, sigma Fy, sigma moment would be just straightforward. Now, this one here has to be explaining a little bit. Apparently, this is intention. Okay? This shear force is minus. What does it mean? Don't forget, we don't actually answer minus value. We answer plus value. Correct? Positive value and then direction. Then we have to change it into plus 60. But what does it mean? That, yeah, it goes up. Yeah. Okay? You're correct. Okay? That one is actually correlate with that box. Correct? The right hand side down, the right hand side down. Your friend is correct. If that one is minus, that one come already, then that one become actually going up. Correct? Therefore here, that one is going up. If that one go up, then that one must come down, opposite. Right? Complete the box. That's all. Okay? Then sigma moment will solve the bending moment, and then that's it for point B. However, I specify point B to show you that actually there's some other way we can calculate it. We don't have to use that picture, right? The same point, this one draw from A to B, from 1 to B, sorry. We can actually draw from B to 2, meaning we can see this picture instead, right? And if we see this picture, the calculation will still be the same. Sigma fx, sigma fy, sigma moment. Exact the same number, exactly the same direction. If you define it correctly. Shear cannot be just up down, it has to be the box, right? Axial force cannot be left right, it has to be compression tension. Bending moment cannot be clockwise or anti-clockwise, it has to be smiling or sad face. It will be the same. You don't have to, I repeat myself, you don't have to use both body. You can choose one of them. Which one should you choose? It depends on which one is easier. The two pictures give you the same numbers. It's up to you, but for me, I will choose the right hand side picture any given day. Less force, less calculation, less terms. Okay, but you might not like the angle. You might think more force with no angle would be easier for you. Fine, it's up to you. It ends up the same answer if it's correct. So this is summary for our example 1. Now, up to this point, I should remind you again. In the first half, 3 equations give you full marks, right? Sigma fx, sigma fy, sigma moment. For one free body diagram, that's a somewhat full mark already. In the second half, this one here, you need 9 equations. Still the same, sigma fx, sigma fy, sigma moment. So be really, really good at it, quickly. This one per question, you're still given the same amount of time. And I'm not joking. Okay. Next, this one here will actually, the reason I have to do this because 2 things. One thing is that we have to make sure that you understand it is more about where the element line. X is not horizontal, vertical. X, in this case, X will be this line for N, for V, and for bending moment. Secondly, apparently we have to actually sort out the picture of 90-degree angle to the force to get the moment. Okay? So you're going to see more of this really soon. It's fun. Right? Oh, sorry. The key is here. The key is this force is 90 degrees to the member. Okay? It's said here. And it said point A, it doesn't give distance, but it said point A is in the middle of it. In the middle of the beam. Meaning that one measure down here 1.5, right? If we measure that way, 2 meters. Okay? The whole beam length is 5. Therefore that one to that one is 2.5. That's all, just in the middle of the beam. Okay? The first step, as usual, reaction first. Okay? Now, by this, I think we start to get this system. Okay? So we'll take moment at this point. Right? We should get R2. The equation, let me explain a little bit. I will use direction of R2, rotation anti-clockwise positive. Okay? This force pressing down here, it rotates clockwise. Correct? Right? Therefore minus. The total force is the magnitude times the whole length it covers. So 60 times 5. Right? Now, how do you calculate moment? It is the force times 90-degree distance. Correct? Now, this force here will point down according to these arrows. Meaning it makes 90 degrees with this line already. Correct? Therefore, there is no need for you to take in the x component, y component, because we know that from here, that one here, the centroid of this area is in the middle, correct? Meaning it's actually in this case for at point A, exactly. From here to here is 2.5 and is already 90 degrees, right? So that's the one. Am I clear enough? Is that correct? Right? If this line here is 90 degrees, then that has to be 90 degrees. Right? Therefore, that one there is 2.5 meters already. Right? So there is no need for me to take that component times this distance and then that component times this distance, because the force and distance is already 90 degrees. Okay? So that's the meaning of it. Now the second part is R2. R2 is not in inclined angle. R2 is just vertical. Therefore, 90 degrees distance is horizontal, meaning from here to here, 4 meters. Okay? And then we can have R2. If you take component, it will be much longer, believe me. It will end up the same answer though. So it's up to you. Okay? Next, sigma fx, sigma fy will give you other point, other part. This part, it looks a little bit strange. However, I will leave you to work out how it comes from, where it comes from. Okay? It's about the relationship between triangles and its sides, 90-degree triangles. But then once we get that, what do we do? Then we look at cut at point A. If you wonder what it is, we can discuss after in the second hour. Okay? Let me continue with the answer, with the solution for now. Right? The same thing. Again, I can look at the top picture. I can look at the bottom picture. I can draw from 1 to A. I can form from A to 2. It should give me the same answer. Okay? Once I draw it, because I know this time I will have to take component of the forces. So I start giving the angle. I will call that angle theta. If that is theta, then that must be theta as well. Remember the alternative angles we discussed? It is still that idea. Okay? Now, if I decide that is theta, can I ask you what is sine theta? Three over 5, 0.6. Okay? It's the ratio of the triangles. This is 3, 4, 5 triangles still, right? Okay, so that's understandable. Now, rather than do sigma fx, sigma fy, which I will have too much unknowns, what I do is I will take forces in this line instead, which I call sigma fn. Meaning when I do that line, this one is 90 degrees, I don't have to think about it. Right? This picture, if you do sigma fx, sigma fy, you still get the answer. But you need to solve two equations, two unknowns. Your choice. Okay? I always do this way. Okay? If it's sigma fn, then I have NA. That one doesn't count, moment doesn't count, that one doesn't count, 90 degrees. Correct? N is on the line of the member, that force is 90 degrees to the member, therefore 90 degrees to N as well. Then that one has to take component. Into that line, it must be sine theta. Correct? There, sine theta. Okay? Then we get the answer. Then of course, since we do sigma fn, the next one we probably do sigma fv. The same idea. If it's sigma fv, NA doesn't get involved, bending moment doesn't get involved, that one positive, that one then negative. 60 doesn't cover 5 meters in this picture. This picture is only 2.5, correct? From here to here is 2.5. Therefore, that 2.5. And then that one has to take that component which is cosine. It happened to be 0. If it's 0, then we don't keep the sign convention. We don't keep the direction. We just keep the unit. That's it. Sigma moment, the same way I take moment about this point. 60, cover 2.5, halfway is 1.25. That's the moment. That 1.7 is vertical. Correct? Therefore, distance I can use horizontal, 2 meters. You can take 187.5 cosine times 2.5. You can do that too. But it's longer. I don't know why. You should. Okay? So, before you calculate the moment, always ask yourself, this is easier for you to get the 90-degree distance rather than take component of the forces. Okay? The key is 90 degree. Notice the smiling. This time the smiling is no longer vertical. Okay? Meaning it has to be in inclined angle as well. Okay? That's it. Summarize. There we are. Questions? No, just 6 equations. Simple. The calculation, if you can see the picture clearly, the calculation is never very long in this subject. It tends to be about 3 terms, 4 terms max. Okay? And each term tend to be simple number, just time each other, plus minus, that's it. Okay? Any questions? If not, then let's enjoy our break for 10 minutes, okay? See you guys back here in 10 minutes. Listen, the time is up. There's something that I'd like to point out before I leave you guys. I have a question, okay? Since we can calculate from any way possible, point A is here, point B is here. Once I do sigma m1, I have R2. Do I need R1x, do I need R1y or not? If my target is to find internal forces at A and at B, do I need R1x and do I need R1y or not? In fact, I don't. Once I calculate this picture, when I want that point, I cut that part out and then draw from B to 2. If I want point A, I cut here and then I draw from A to 2. I do not see R1x, R1y at all. Okay? So, think carefully whether you need to calculate all reactions or not. You tend to need reactions, but sometimes you don't need all of them. Okay? So rather than having to do 6 equations for this question, you may need only 4, for example. Okay? Think about it. Then I think that is for today. Oh, I see you guys tomorrow morning. Right? Okay then. Thank you very much. Oh, I see you guys today at 2. Right? Okay then. See you in a bit then. Okay?